In this part of lecture for chapter 7, we're going to talk about how to classify the chemical reactions. Up to now, we've learned how to write them and how to balance them. But there are different kinds of chemical reactions, and it is helpful to know to what class they belong. The first class we're going to talk about are called precipitation reactions. These are reactions that form a precipitate, a solid that will fall out of solution. Solute, which is what is being dissolved in the solvent to make a solution, they can precipitate out of solution when their concentration is larger than their solubility. So if we add more, let's say we add a little bit of solute and we dissolve it in a solvent, and it dissolves, and then we keep adding more solute, we keep adding more to it and dissolving it. There comes a point where there's enough of that solute in the solvent that has dissolved, and if we add any more, there won't be any solvent left to dissolve the solute, because all the molecules of the solvent are actually involved in dissolving what solute is already there. Therefore, if we add more solute, that solute is just going to precipitate. It's going to fall out of solution. It's not going to be dissolved anymore. And that is because that concentration, we've added more solute than what its solubility dictates. This is when a precipitate forms. It is very helpful to understand how to use what is called a solubility table. This is a very condensed one, but I don't really expect you to memorize all of these, but you certainly should know how to use it. For example, let's see, on this side here are the rules, and here there's the exceptions to those rules. Let's take rule number 1. Group 1 metal cations, so lithium, sodium, potassium, rubidium, cesium, etc., and ammonium ions, so compounds that contain these metals, these positive ions, are always soluble, always. There is no exception to that rule. So every time, even if these metal cations are paired up with anions that are not soluble, like these down here, they will still be soluble because they're paired up with these positive ions. So learn to recognize these ions and in ionic compounds or salts, and if you see them, you will know that that particular compound is soluble. What about this rule, the halide ions? This is group 7 ions. These ions are always soluble unless they are paired up with silver, with mercury, and with lead. So if I have sodium chloride or calcium chloride or magnesium chloride, those are soluble. But if I have silver chloride or if I have lead 2 chloride, those chlorides are not soluble because these are exceptions to the solubility of the halide ions. The halide ion fluorine is soluble except for the fluorides of group 2 metal cations, so calcium fluoride, magnesium fluoride, etc., and lead and iron 3 fluoride. So if you see fluoride paired up with group 2 ions, metal ions, and or lead and iron, then that compound is not soluble. If you have the acetate, bicarbonate, nitrate, and chlorate ions paired up with anything, those are always soluble, just like the group 1 metal cations. If you have these 4 anions as your anions in the salt, in the ionic compound, then that means that those compounds are soluble. There's no exceptions to those rules. even if they're paired up with lead or iron or mercury or whatever. If they have these 4 anions, then they're soluble. The sulfate ion is typically soluble unless it's paired up with silver, barium, calcium, with mercury, lead, and strontium ions. These ions over here. So these are the exceptions to the solubility of sulfate. So if you have sodium sulfate is soluble, but if you have barium sulfate, that's not soluble because barium is one of the exceptions to the solubility rules. Here's the insoluble compounds. Insoluble compounds: carbonates, chromates, phosphates, sulfide, hydroxide. So typically these anions, so compounds that contain these anions, are insoluble, except for those. So if these anions are paired up with group 1 metal cations and ammonium ions, so these here, and the hydroxides of group 1 metals and barium 2+. So barium hydroxide is soluble. Sodium, lithium, potassium, rubidium, cesium hydroxide, ammonium hydroxide, it's soluble. But calcium hydroxide is not. Magnesium hydroxide, iron 2 or iron 3 hydroxides, etc., etc. This is how you go about thinking of the solubility table rules. Look this over and practice a few of these. They become easier as you practice. I have included a bunch of problems here, and I've made 2 videos, one that includes these first group and this second group here, to give you some practice and show you how to write precipitation reactions if you're given the reactants, how to write the products, how to balance the equation, and how to determine which one is your precipitate, if there is any. And then in the second group here, I have illustrated how to actually write the reactants first, then come up with the products, balance the equation, and figure out the precipitate if there is any. Look these over. If you want to try these on your own first, that's fine, that's great. And then compare your answers to what I have. If not, you can watch the videos for a few of these and then try to halfway maybe through, you can try your own hand at these. But either way, you can watch these and learn how to do them. If you need more practice, go to the back of the chapter or on the internet. There's tons of these types of problems. Precipitation reactions that we just covered are also known as double replacement reactions. The double replacement meaning that I am replacing 2 ions with each other, not just 1, but 2, and that's where the double comes. As you can see here in this reaction, to come up with sodium nitrate, what I'm doing, here's my nitrate as on the reactant side, I'm replacing my silver with sodium to form sodium nitrate, but I also replaced sodium here with my silver to form silver chloride. And remember the rule, chlorides are soluble except when they are paired with silver and lead too, and therefore this is my solid. So precipitation reactions are also known as double replacement reactions because I'm doubly replacing the 2 cations. I'm flipping these 2, if you will. The next set of reactions that we're going to talk about are acid-base reactions. These reactions are those reactions when I have an acid reacting with a base. These are reactions in which a hydrogen ion is exchanged from the acid to the base. In this example over here, if I have HCl, hydrochloric acid, and I put it in water, water can act as a base, and what I have is the transfer of this hydrogen ion from the HCl species to the H2O, to the water to form, and now because it's got an H+, it becomes H3O+, and then I have left behind my Cl-. If you have a strong acid and a strong base reaction, what you will have is the formation of water. They're called neutralization reactions, and that only happens with a strong acid and a strong base. Strong acid like HCl and strong bases are bases of group 1 metal ions, such sodium, potassium, lithium, etc. So when you have those types of acid-base reactions, you will have complete transfer. You will have a formation of a salt, such as NaCl, and then water, and therefore you have complete neutralization of the acid and the base. That's why they're also called neutralization reactions. The next set of reactions we're going to talk about are oxidation-reduction reactions. In these types of reactions, unlike the acid-base ones, we don't have the exchange of the proton or H plus ion. Here we're transferring electrons from one species to the other. This happens a lot with metals. And what happens, because we have the electrons that are being transferred, we have a change in the charges of the elements or oxidation states. Here's a simple example of a redox reaction, reduction oxidation reactions. We have sodium metal reacting with chloride or chlorine gas to give me sodium chloride solid. What I have here is a change in the oxidation states of these elements. Anything that appears in its elemental form, such as sodium or chlorine, has a zero charge. They are neutral atoms, neutral elements, and therefore they're not charged, so they have a zero. Sodium, for example, is going from a zero charge to NaCl, which is a +1 charge over here. We can express these as half reactions. Reactions that deal only with one element at a time, one change in oxidation at a time. Therefore, I can take sodium from metal with a charge of 0, and it yields sodium ion as a product here, as a +1. Now, because I have two sodiums, I transfer 2 electrons. I lose 2 electrons. If the oxidation state of the element of the species is getting more positive, that means that it is losing the electrons, and they appear on the product side because it's losing. Sodium is losing the electrons. They are made as product, if you will. When that happens, so loss of electrons is called oxidation, and oxidation is accompanied, as I said, with an increase in positive charge. Your species becomes more positive because it is losing negative charge, it's losing electrons. The opposite is true for reduction. Reduction is the gain of electrons. And if I'm gaining electrons, I'm gaining negative charge, which means that I'm becoming less positive or more negative. Chlorine here also has a 0 charge, and it's gaining electrons and going to chlorine minus, the anion. Therefore, I went from a 0 to a -1. I'm becoming more negative or less positive, which means I'm gaining negative charge. I'm gaining electrons. Now you can see that the number of electrons transferred has to be equal, because I cannot have more electrons or less electrons on one half reaction than the other. Those electrons that sodium metal loses are gained by chlorine gas. I cannot have free electrons floating around here. Therefore, the number of electrons on both sides here has to be the same. Here's once again, another half reaction for this particular, so these are the half reactions for this total reaction over here, where I have silver bromide going to silver solid and bromine gas. Here we have a salt, silver has a +1 charge and bromide is a -1 ion. And silver here is a 0 charge because it's in its elemental form, and bromine is in its elemental form, so it will have a 0 charge. Therefore, silver is going from a +1 to a 0. It's becoming less positive. Because it's becoming less positive or more negative, it's gaining electrons, so it's being reduced. Bromine is going from a -1 to a 0, which means it's becoming more positive. And because it's becoming more positive, it's actually losing the electrons and it's being oxidized. Note that for whatever species is being reduced or gaining the electrons are going to appear on the reactant side. For those species that are being oxidized, like bromine here, they lose the electrons, therefore the electrons are going to appear on the product side of the half reactions. And then if I add these two reactions together, anything that appears on either side or on opposite sides of these arrows can be canceled if they look exactly the same. And then what I have is a net total reaction. If I add these two together, what I can cancel are these 2 electrons over here with 2 electrons over here because they appear exactly the same but across on opposite sides of this arrow. These 2 electrons are on the left-hand side and these 2 electrons on the right-hand side of arrows, so I can cancel them. And then what I have left is 2 silver plus ions plus 2 Br minus ions, giving me 2AgBr2. These are half reactions, and it's another example on how to write them. I have made videos of how to balance and write half reactions for these 3, so 3 more examples for you. Watch these videos and see how it's done. Hopefully you'll be more comfortable. If you have any questions, let me know. If you need more help, you can look, or more examples, look in the back of the chapter, or you can reach out to me and I will send you some more examples if you want more practice. Okay, the last reaction that we're going to talk about is combustion reaction. These reactions are those types of reactions where you will know that it's a combustion reaction because it will have oxygen as one of the reactants, and then it will have CO2 or H2O. It might have other products, but you will at least have CO2 and H2O on the product side. So oxygen on reactants, CO2, H2O at least on the product side. And you know, whenever you see combustion, that means you're reacting something in oxygen. It releases CO2 and H2O and a lot of heat and light. This is basically burning. Whatever burns, this is ethane gas, but you can have wood, you can have anything that's combustible that reacts with oxygen, and it will give you eventually CO2 and H2O. It might give you other products as well, but these are the 3 things that you should look for a combustion reaction: oxygen on the reactant side and CO2 and H2O on the product side. The single replacement reactions we already kind of talked about. Single replacement reactions are also redox reactions, but in these types of reactions, what we're doing is we're taking we're replacing only one of the ions, not both, like the double replacement reactions or precipitation reactions. For example, here I'm taking the copper and I'm inserting it. I'm replacing silver to give me copper 2 nitrate and silver solid. So I only have one replacement instead of a double replacement. This is also a redox reaction, and we already talked about it, because copper is going from 0 in its elemental state to a 2+, and silver is going from a +1 to a 0. So you have loss and gain of electrons. You have a redox reaction. Okay, that concludes this part of the classification of chemical reactions. And the next part we're going to talk about is stoichiometry. Very, very important, very widely used in chemistry.